this video, let's look at this electrophilic substitution reactions of benzene of the BSC first year, that is from the chapter Aromatic Hydrocarbons. Let's look at each one of these reactions in detail. The first one is the nitration of benzene. We have seen the general electrophilic substitution reaction mechanism in my previous video. What are the general electrophilic, what are the electrophilic substitution reactions that benzene will undergo actually are nitration, sulfonation, halogenation, and Friedel-Crafts reactions. We are going to look at this nitration, sulfonation, and halogenation in the first video. And my next video, I'm going to discuss about this Friedel-Crafts reaction. So when we come to the nitration of the benzene, actually, yes, the benzene undergoes nitration with a mixture of concentrated sulfuric acid and nitric acid at 50 to 60 degrees centigrade actually. So we should take a mixture of concentrated sulfuric acid and nitric acid. Then we are calling this as a nitrating mixture here, which will help us, which will bring about the nitration of this benzene. So the substitution reaction is occurring where the H of one of these carbon atoms is being substituted by the NO2, and that is the overall substitution reaction which is occurring here. Here, if you just take the hot concentrated nitric acid here, yes, here explosion reaction might occur because here the concentrated nitric acid reacts with any oxidizable material. This might explode. Right. So we are taking a mixture of concentrated sulfuric acid and nitric acid, where sulfuric acid is acting as a catalyst here, and which allows the reaction to take place more rapidly and at a lower temperature itself. So at the lower temperature itself, the reaction will occur because the sulfuric acid is act as a catalyst here. So sulfuric acid is what acting as a catalyst, where the reaction occurs more rapidly and at a lower temperature itself, and will not allow the reaction to explode or the explosion reaction occurring. Right. So when we look at the mechanism of this nitration reaction, it occurs in 3 steps. First is the generation of an electrophile. Second is attack on the electrophile forming the sigma complex. And third one is loss of proton from this sigma complex, giving you the final product, that is a nitrobenzene. First one is generation of an electrophile. So in this generation of an electrophile, here first we should, this nitric acid, the overall reaction actually reacts with this sulfuric acid, where sulfuric acid is providing a proton for this, so resulting in this nitronium ion, which is the attacking electrophile actually, and water plus HSO4 minus. So here, first of all, this is a sulfuric acid and this is nitric acid, HNO3 here. So what is happening here? So this one sulfuric acid is protonating this nitric acid actually. So sulfuric acid protonates the hydroxyl group of this nitric acid. So protonates the hydroxyl. This oxygen is getting protonated. So thereby there's a positive charge on this oxygen, and HSO4 minus is being generated. So this protonated nitric acid in the next step here releases water. So this double bond is shifted towards this oxygen, thereby giving water, and here the lone pair of electrons on the oxygen again shifted. So resulting in the formation of this nitronium ion, which is strongly electrophilic in nature. There's a strong electrophile now which is generated. Right. So here what is happening, the overall reaction is where sulfuric acid is protonating the hydroxyl group of this nitric acid, where water is released and the nitronium ion is generated, which is acting as a strong electrophile. And in the second step, this nitronium ion gets attacked by this pi electron cloud of this benzene ring. You know, this is electron rich. So This will attack on this nitronium ion because this is electron deficient and this is a strong electrophile, wherein this first step is a slow step and this is a rate determining step of the reaction, resulting in the formation of this carbocation intermediate, where we are calling this as a sigma complex or arenium ion, whatever. So this is a sigma complex which is being formed. So here the carbocation intermediate. So we can see the resonance stabilization of this carbocation intermediate. So we can show the resonance hybrid also of this here. So resonance hybrid which is being formed here. So this is a sigma complex because we are calling it as a sigma complex because there is a new sigma bond which is formed, that is between the electrophile and the carbon atom of this benzene ring. There's a new sigma bond which is being formed. That is why we are calling it as a sigma complex. And we know that this is the first step, is a slow step of the reaction, and it is what endothermic reaction. It's an endothermic reaction here because energy is taken in for the formation of the sigma complex here. And the second step where it is losing its aromaticity, loss of aromatic character. If you can see here, aromatic character is being lost. Because this one, all are sp2 hybridized in the benzene ring. But if you look at it, this is sp3 hybridized. So loss of aromatic character and also 4 electrons now. Overall, there is a loss of aromaticity and the reaction is endothermic in nature. And this is a slow step of the reaction. So this is a rate determining step of the reaction, if you can see here, resulting in the formation of an sigma complex. And in the third step, the loss of the proton here, giving you the nitrobenzene. So proton is lost to the HSO4 minus. So here HSO4 minus, this H2SO4, giving you the nitrobenzene. So this is the mechanism of nitration of benzene, where overall you can say that the benzene here reacts with nitric acid in the presence of sulfuric acid, where it is acting as a catalyst, where we are calling this as a nitrating mixture. And one of the hydrogens of this is getting substituted by the nitronium ion, giving you the nitrobenzene. And this step is a fast step, and it is the exothermic reaction where the heat is released in this step, and also the aromaticity is regenerated, right? It is regenerating the aromatic character. Because the sp2 hybridized carbon, sp3 hybridized carbon atom has now changed to sp2 by the loss of proton, thereby it's regenerating its aromaticity. So this is about the nitration of benzene. When we come to the second reaction, that is the sulfonation of the benzene, here the sulfonation of the benzene can be carried out with the help of fuming sulfuric acid. It's carried out when benzene is heated with fuming sulfuric acid. So what is fuming sulfuric acid here is 7% SO3 in H2SO4 is called as fuming sulfuric acid here. So here, if you can see that this reaction actually is reversible in nature. So benzene reacts with sulfuric acid, where actually the attacking electrophile, if you can see here, it is the SO3. The attacking electrophile is SO3 in the presence of H2SO4, if you can see, is giving you benzene, sulfonic acid, and water. Right. So this is the reaction actually, which is seen here. So first is again the first step is the generation of the electrophile, where you can see the attacking electrophile is the SO3 here, which is formed from sulfuric acid, giving you sulfur trioxide, H3O plus and HSO4 minus. Again, right. So here again, when you see the second step is the attack of the attack of this benzene ring. There's a pi electrons of this benzene ring on the sulfur trioxide, resulting in the formation of a sigma complex again. So this is a sigma complex which is being formed, and we can see the resonance stabilization also of the carbocation here. So this is the second step. This is a slow step of the reaction, the rate determining step of the reaction, where the rate of the reaction depends upon this second step. And the third step is the loss of the proton here. So proton is lost, thereby aromaticity is also regenerated here. And again, the proton here, reprotonation of this oxygen atom, giving you benzene sulfonic acid. So this is the second step where proton is lost here. So resulting in the formation of this product, and then this proton reprotonation of this can occur, resulting in the formation of this benzene sulfonic acid. But the third step is again the fast step here, where the rate of the reaction does not depend upon this. And the third reaction, as we have seen, this nitration sulfonation. Now this is a halogenation of benzene. Halogenation, we can see reaction with the chlorine, bromine, and iodine also we can see here. Right. So again, if you see that for the halogenation of the benzene to occur here, it is necessary for the use of a catalyst here. So which catalyst? The Lewis acid catalyst is used here, like AlCl3, FeCl3, FeBr3, or ZnCl2 should be used as a catalyst for the halogenation of the benzene. So the overall reaction is benzene plus the halogen, that is either Cl2, Br2, or I2 in the presence of catalyst. This catalyst is nothing but the Lewis acid catalyst. So we are using the Lewis acid catalyst like AlCl3 or FeCl3 or FeBr3 used as a catalyst, resulting in the formation of halobenzene and H's. So why this Lewis acid catalyst should be used in the chlorination? Yes, so we should use this Lewis acid catalyst because the halogen itself is not a strong electrophile here. Because the halogen we are using is not sufficiently electrophilic here to react with the benzene. So to make it sufficiently, strong electrophile, there we are making use of this Lewis acid here. So whereby the reaction with this Lewis acid, with this catalyst, generates a strong electrophile which can react with the benzene. So let's see this, how it is happening. So first look at the bromination of benzene. So in the bromination of the benzene, so we are using a Lewis acid catalyst, this Br2, which is not strong electrophile. So here, what is happening here? So we are making use of the Lewis acid catalyst like FeBr3, right? So this is what Lewis acid, which can accept the electrons. So here, this will accept the electrons from this Br2, so resulting in the formation of a intermediate, catalytic intermediate, which is being formed here. With the partial negative charge here and the partial positive charge on the Br, on one of the bromine atoms. So what will happen, this is called as catalytic intermediate, which is being formed here. So because this bromine is not sufficiently electrophilic, because it is not a strong electrophile, that is why we are making use of a Lewis acid catalyst here. Thereby we are generating a strong electrophile which can react with benzene. Okay, right. Here bromine donates a lone pair of electrons to Br3, which weakens the Br bond here, thereby generating a partial positive charge on one of the bromine atoms. So the second step is attack of the electrophile forming a sigma complex again. So yeah. So forming a sigma complex where the attack of this pi electron cloud of the benzene ring on the electrophile. So this is a strong electrophile here with a partial positive charge at one end and partial negative charge on the other end of the catalyst. So no, this is a positive and this should be a negative. Because here electrophile is the attacking agent. So this is negative. So this attacks on this electrophile here, thereby, yeah. So this is a rate determining step of the reaction, and this is the slow step, so determining step of the reaction here, thereby generating a sigma complex. So here Br and H, so this is a sigma complex which is being formed. Right? So FeBr4 minus. So we can write the carbocation intermediate also with resonance structures. So this is a resonance hybrid. This is a sigma complex which is being formed here. So the third step, it can lose a proton. That means the loss of the proton from this sigma complex, thereby giving the product. So this one is H, Br. It's a positive charge here. So this is acting as a weak base here, thereby abstracting a proton. The proton is lost to FeBr4, thereby regenerating the aromaticity with the substitution, that is the bromine on the ring plus HBr, and catalyst is regenerated, that is Lewis acid. So here in halogenation reactions, we are making use of the Lewis acid catalyst because this halogen is not strongly electrophilic to react with the benzene. So to increase the electrophilic nature of this halogen, we are making use of this Lewis acid catalyst. So if you look at the chlorination also, chlorination reaction of this benzene, this is also similar to that of this bromination, where we are using the Lewis acid catalyst here, FeCl3. Benzene plus Cl2 plus FeCl3. Chlorobenzene is being formed plus HCl. Or iodination also we can carry it out, but this is in the presence of strong oxidizing agent here. We are using here acidic oxidizing agent here. So this is acidic oxidizing agent like HNO3 we are using here to carry out the reaction, whereby here the attacking electrophile will be I plus iodonium ion. Iodonium ion. So how is the reaction occurring here, whereby we are using the oxidizing agent like HNO3 in the presence of iodine will give you iodobenzene. So these are the reactions, that is nitration, sulfonation and halogenation of benzene. Next video I am going to discuss about this Friedel-Crafts reactions. If you like my video, please do like, share and subscribe my channel, and the whole chapter has been discussed on my YouTube channel, and the link of it is given in the description box below.